Hi everyone! In this demo video we present to you our IoT project, a smart greenhouse. The idea is to provide a simple solution for those who want to grow their own vegetables directly and comfortably at home, managing everything through the smartphone. This way, even if you are away from home, you can have real-time updates on the status of the greenhouse, change settings, and view graphs on the measurements of the past few days. Two protocols have been used for the communication among the stakeholders, MQTT and REST. For MQTT protocol, we use the message broker for publishing on the specific topics, data coming from the sensors, and possible actions to perform, and for subscribing to these topics to retrieve the information. The second one is the REST protocol, that consists of making HTTP requests to a server and receiving HTTP responses in return. The requests and responses use standard HTTP methods such as GET, POST, PUT, and DELETE to retrieve or manipulate data on the server. The use case diagram shows all the main instances involved. The core of the project is the Greenhouse Resource Catalog. Its role is to collect in a JSON file all the information of how to establish the communication among the actors inside the systems by providing them the initial data, like the message broker and port to use, or the Telegram token. The catalog communicates with the main stakeholders in the platform, exploiting the REST methods in order to retrieve all the necessary information and make them available to whoever needs them. For example, by adding new sensors or users, updating sensor threshold, or get generic information. Measurement results will be visible to the user via the dedicated Telegram bot. And in case a device no longer sends signals within 2 minutes, the catalog will take care of removing it from the list of active devices.
In the project, we implemented and simulated three devices: the temperature sensor, the air humidity sensor, and the soil moisture sensor. In each device connector's logic, we instantiate the class of the representing sensor. The notify function is the main function of the temperature sensor's class. It is called after the sensor receives a message on an MQTT topic from the control strategy containing the value of the computed PWM. Thanks to this value and other parameters, it is able to compute the new temperature, which is stored in the class variable. The new computed temperature will be then published on an MQTT topic on which the temperature control strategy is subscribed. In the notify function, the new temperature is computed with the following formula, where V is the total volume, dV sub A is the volume of air exchanged with the outside, dV sub O is the volume of air exchanged with the conditioner, sub.temperature is the actual temperature, and T sub A is the temperature of air coming out from the conditioner. The temperature outside T sub O is obtained through the public IP address of the border gateway connecting my local area network, where the greenhouse is placed, to the wired area network, which is Internet. From the obtained public IP address, I will be able to retrieve the city in which the greenhouse is placed, and so the temperature in that specific city. The air humidity constructor instantiates the air humidity value with a random integer number between 0 and 100. This value represents the percentage of humidity in the air. In the constructor are instantiated also two MQTT clients. One used to communicate with the control strategy, and the other one to communicate with TeamSpeak. The first MQTT client is used to save the new humidity value received on an MQTT topic from the control strategy. The second one is used to publish the air humidity value to the TeamSpeak broker in order to have an history of its performance. For what concerns the soil moisture sensor, it behaves in the same way of the air humidity sensor. Summarizing, the device connector communicates with the resource catalog, the control strategies, TeamSpeak, and finally with Telegram bot.
In order to control the temperature, the air humidity, and the soil moisture value of the greenhouse, we built three control strategies. The temperature control strategy is meant to receive a desired temperature value through a put request and generate a PWM signal sent to a specific topic through MQTT protocol. The PWM is used by the device connector to control an heating element. In our case, the heating element is simulated as an air conditioner that is able to blow air at a temperature that goes from 10 to 40 Celsius degrees. The PWM is computed by a PID controller that links the PWM value to the error between the desired temperature and the current one of the greenhouse that is received through MQTT protocol. So the PWM is the sum of the error, its integral, and its derivative. Each action is multiplied for its own proportional coefficient. These coefficients are computed with an algorithm that we wrote with the aim to minimize the square error of the temperature and find an optima using a package called Gecko. The PWM value is bounded between 0 and 1 since it is a percentage. Therefore, through a GET request, the control strategy can return the current value of the threshold or if it is set to the off status. The soil moisture control strategy receives the desired soil moisture value through a put request and the current soil moisture value through a GET request. If the current soil moisture value is more than 3 points lower than the desired one, the water pump is turned on through an MQTT protocol. When the soil moisture reaches the desired value, the pump is turned off. With the same strategy, the air humidity is controlled by turning on or off a fan. All the control strategies communicate with the greenhouse catalog through HTTP to get the message broker for the communication through MQTT protocol and the device ID for the specific sensor each strategy needs to communicate with. They also communicate with the Telegram bot and the Greenhouse app, exposing a REST APIs to change or return the value of the threshold. Another service used in this project is T-Speak, that is an IoT analytics platform that acts as a database to store the measurements collected by the sensors and display them in charts. Those charts are shown in the Telegram bot or in the app when it is requested by the user. Device Connector communicates with TeamSpeak through MQTT protocol to send the collected measurements. It also communicates with the Telegram bot and the app through HTTP requests to send the charts of current day, last 2 day, or last week measurements, and with no thread to elaborate them.
Node-RED is a programming tool for wiring together hardware devices, APIs, and online services in new and interesting ways. In this project, it is used to retrieve data about temperature, air humidity, and soil moisture from TeamSpeak, exploiting REST APIs, and to visualize them in the form of graphs. Also, the threshold values set can be viewed in the form of level gauges. To improve the user interface, a Telegram bot has been implemented. In particular, the user can use the bot to set the temperature, humidity, and soil moisture threshold. He can be updated about the greenhouse parameters and also retrieve dashboard to get an overview in the specified interval of time. 3 time windows are available: today, last 2 days, and last week. To allow the interaction between the user and the greenhouse, few commands are available on the bot. After the smart greenhouse is launched correctly by using the start command, the user can retrieve the current value of each sensor by using the proper commands. Also, the value of the thresholds can be seen. Specifically, either a numeric value or off can be displayed on the chat, depending on the device being switched on or off. In addition, the user can visualize different dashboards for each sensor depending on the chosen time window. In particular, 3 inline keyboard buttons will appear after sending the dashboard command to allow the user to choose a time frame in which to view the data. Finally, the user can set the threshold values of the sensors. In this case, a message will be shown in the chat, and the user can specify the numeric value of the threshold. After this, the algorithm checks if the value is of the proper format, and if not, an error occurs. It is also possible to write off if the user wishes to turn the sensor off. As regards the communication between Telegram and the other actors, the main ones happen between the catalog, TeamSpeak, and the device connectors through REST communication protocol. In particular, the communication with the catalog is important to register the bot token. The communication with TeamSpeak takes place to retrieve the data used to create the dashboard shown in the bot. Finally, the communication with the device connector is essential to get data from the devices registered in the catalog or to send data from the bot to them. In addition, we implemented our Greenhouse app by exploiting the KiwiPython framework. It provides the same functionalities of Telegram bot, and also the communication with the other actor is similar. The only main difference is that our Greenhouse app needs to communicate with an app adapter through MQTT protocol. This enables the communication through REST between the app and the sensors running in local network. Thanks for your attention.